I wrote down.
Yeah. And so do you know if your teacher's going to give those to you on the test?
I don't think so.
Yeah. Okay. So this is where I always remind students, it's your responsibility to remember them. And hopefully you can figure out a way. So the problem with this is that you're taking the variable derivative with respect to two variables, which is no good. So you have to figure out how, volume and radius are related. Usually you end up drawing a triangle, kind of a slice cross section of it. You've got the height, and then the whole height is 10, and then you have the radius, and then the whole radius is 4, like that.
Hmm.
You could set up some sort of proportion here for that. You could say like r over 4 equals h over 10, and you can solve for whichever variable you want to get rid of. So you wanna solve for r because you're trying to find h prime. So we cross multiply here. We get 10r equals 4h, and then r equals 4 over 10 times h, 2/5 h. So that goes back into your volume formula.
Hmm.
Does that look familiar to you?
Yes, it does.
Okay. Okay. So now you're finally ready to take a derivative. It's in one variable. We got, so let me just rewrite it here. It's 4 over 75 pi h cubed. The v prime is 3 times 4, so you got 12 over 75 pi h squared prime. Is that okay?
Yeah.
Clear? All right.
Hmm.
So they give you the h. They give you the h is 6. They tell you that v prime is 5. You solve for h prime here. So you can either put the numbers now or later. Which do you prefer?
Uh, Probably now.
Okay. 5 equals 12 over 75 pi 6 squared h prime. So you're going to multiply by 75 on both sides. What is that? It's a lot. 375 equals 12 pi 6 squared h prime. So you divide by that. I guess this doesn't really work. Anyway, it's whatever that is over 12 pi 6 squared
Hmm.
um, to get your h prime. And then units. Units are very important. It's asking how fast is the water level rising. That's feet per minute. Feet per minute. Any questions on that?
No, I don't think so.
Okay. Number 2 then.
Yeah.
All right. A hot air balloon is rising from a level field. It's tracked by a rangefinder 500 feet from the lift off point. At the moment, the rangefinder's angle of elevation is pi over 4. So I'm having a little trouble figuring out how to draw this, but we know that this angle is pi over 4. What I can't tell is where the 500 goes.
I'm pretty sure the 500 isn't the height, it's the base. Or that's what I was
Okay.
told.
Yeah. Um, it's not written well. That's why it's difficult to figure out.
It's not the
And the
best.
angle, yeah, and the angle here. So this is theta. Theta prime is 0.14 radians per minute. And so what are we trying to do here? We're trying to figure out how fast is the balloon rising at the moment. Okay. So we need the height, and the height you can calculate using trig. You can do the tangent of theta, the tangent of pi over 4 equals h over 500. H equals 500 tangent pi over 4.
So how would you like know when to use like tangent to find that? Is it because it
Just by what's given, you're interested in stuff with the height, that's opposite, and then adjacent, you're given. That's why I asked what we thought was 500.
okay.
So tangent pi over 4 is 1, so H is 500. Good, I guess. So the next thing is figure out how fast the angle is increasing. So you're still using this relationship. You're going to write like tangent of theta equals um, the H over 500. But this time you got to take a derivative. Now, the reason we're doing it this way is because you have theta prime. So that's a good thing. You're trying to find H prime. That's good. So what's the derivative of tangent? Let's start with that.
Secant squared.
Secant squared theta prime equals 1 over 500 times H prime, like that. Okay, so we're interested in solving for H prime. If it's not clear why, again, it says how fast is the balloon rising at that moment. H prime is 500 secant squared theta prime. So we know the angle. The angle is pi over 4. We know that theta prime is 0.14. We can quickly calculate this angle here, the H prime. 500, secant squared pi over 4 times 0.14. Are you generally allowed to use a calculator on these?
Yes.
Okay. So, see, most calculators don't have a secant, but you can do a 1 over cosine squared pi over 4. And then units of that, it's feet per minute. Going back to the units from the problem.
I got 140 feet per minute.
Okay, sounds reasonable. Okay, 3 is like this classic ladder problem, very commonly seen on these tests. Right, so the picture is important here. It says a 13-foot ladder is leaning against a house. When its base starts to slide away. So we'll call the ladder here. This is moving out this way. That's X. That's Y. The ladder is 13 feet. By the time the base, 12 feet from the house, that's 12. And it's moving at a rate of 5 feet per second. How fast is the top of the ladder sliding down the wall at that moment? So we're interested in solving for Y prime. Picture really helps here. Okay. Um, so the overarching equation here is that we have x squared plus y squared equals, you call it L squared for the ladder if you want. But we know some of these values, right? We know that the base is 12, the ladder is 13. We can use that to solve for y. Um, how would do you know how to do that? Is that something you need help with?
No.
Okay, so y ends up being 5. It's a Pythagorean triple. And now you go back to this equation, but the ladder's not really changing in terms of its length. The ladder's fixed. You can actually rewrite the equation as x squared plus y squared equals 13 squared. And this is kind of like the related rates. You're taking a derivative and they're both functions of something else. So it's 2x x prime plus 2y y prime equals 0. And then you solve for the one you're interested in, which is y prime, which is minus 2x x prime over 2y minus x prime over y. Then you substitute in the quantities that you have. So minus, excuse me, minus 12 times 5 over 5 ends up being minus 12 feet per second, which is pretty fast.
Okay, and then also, my teacher, he usually does like dx over dt instead of d prime. I kind of
Okay.
like it. I like it as like x prime. Sorry, I like it that way more. But on the AP test, do they usually want you to use like x prime over
No,
dx?
no, it's not out there. So for in a classroom, I would use dxdt because seeing it for the first time, but when you've written a lot of these, you get tired of writing, so you try to minimize.
Okay,
No, that shouldn't matter. Um, that's all right. And I'm happy to use whatever notation you want. I just do reminded. All right.
okay.
So yeah, at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? So excuse me, the area is 1/2 base times height, and we have to take a derivative of this. So a prime, this is a product rule. So it's x y prime plus x prime y, like that. And that's why you need the y prime from the previous problem. So it ends up being 1/2. X value, I think, was 12. Y prime was minus 12. Okay. Plus x prime, which is 5, and y, which is 5 as well. So that ends up being like minus 119 over 2 feet squared per second. The triangle formed by the ladder collapses pretty quickly into no area pretty fast.
Okay.
Oh boy, even more. Wow, jeez. Part C. Can't get over this thing. All right. At what rate is the angle between the ladder and the ground changing? There's the angle. You don't have to use you can use the fact that the ladder is there. I would. Like I wouldn't use tangent, I would use um cosine or sine. So if you use like sine of theta, which is y over L, when you take the derivative, there is sine is cosine theta, theta prime. This is really 1 over L times y. The 1 over L is a constant because the ladder isn't changing. It's
Mhm.
1 over 13 y prime. It's a little bit easier to calculate that. So the derivative here of theta prime is y prime over 13 cosine theta. So we were told that the angle, we don't know the angle, so we have to calculate the angle. So cosine of theta is 5 over 13. Actually, we do know y prime. Y prime is minus 12. 13 times 5 over 13 ends up being minus 12 over 5. How was that for you?
I understand that one.
Okay, right. These are almost all, well, I guess they're related rates. We got a couple more here. So you have a test on this tomorrow?
Not tomorrow, it's next week.
Next week, okay. All right. So number 3 says rectangle has its base on the x-axis and its upper vertices on the parabola y equal 12 minus x squared. what is the area the rectangle can have and what are the dimensions? So there's a rectangle in here. And so the base is x and x. The base is really 2x. And the height is 12 minus x squared. So how do you find the area? The area is base times height, which is 2x times 12 minus x squared, like that. So the picture is key. Recognize that it's x and x. That's key. They can use different functions sometimes. The height is almost always the y value.
Mhm.
Okay, so we wanna take a derivative here. It'd be better to simplify, so it's 24x minus 2x squared, which is, now you gotta take a derivative. Derivative of this is 24 minus 4x. Be right back with you. All right, so I gotta set it equal to 0. So x ends up being 6. Now, do you guys have to show that that's min or max, either with the first or second derivative test, or you just good to use it?
I don't think so.
Okay, so that's x. Well, that doesn't seem right. Yeah, that isn't right. Just 12 minus 6 squared is a negative number. Did I miss yeah, I missed that's why. Okay, that's one reason why I'm not feeling well. Missing stuff like that. So that's 6x squared. That's why it wasn't right. It ends up being 2 plus or minus 2. It's 2x cubed, 6x squared.
All right.
Okay, so we're now we define y. Y is 12 minus x squared. 12 minus 2 squared, which is 8. So those are the dimensions. X is 2. The base though is 2x, so that's maybe what they're looking for. Base is 2, the height is 8. And the area is 4 times 8, which is 32. What do you think about that?
I understand that one.
Okay, number 4. These are all classic problems. Like, these aren't weird ones.
Hmm.
Like these are all expected to be. None of these are on the AP. So by the way, they don't leave weird stuff on the AP. These would appear like though in a regular calculus class at college. So you're designing a rectangular poster to contain 50 inches squared of printing with 4-inch margin at the top and the bottom, 2 inch on each side. What overall dimensions will minimize the amount of paper used? 50 inches squared of printing. Okay, so we have y and x. X times y is 50. 4 at the top, 4 at the top, 4 at the bottom. That makes this y plus 4. And then the other way is 2 inch on each side, 2 and 2. So it's x plus 4. So it's y plus 8. And then x plus 4 on the bottom. Does that match up with how you see it?
Hmm.
A better drawing would help. I've not made a very good attempt here, but that would help. So the area, the total area of the poster is y plus 8 times x plus 4. Since we only want in one variable, we're going to solve, this equation up here for y, probably. That's the more standard one, 50 over x. And 50 over x plus 8, x plus 4. So this becomes, I would multiply it out, I guess. I wouldn't try to do it I wouldn't try to use product rule. I would multiply this out. So it becomes 50 plus 200 over x plus 8x plus 32. So it's a prime is minus 200 over x squared plus 18. Set that equal to 0 and solve for x. So a little manipulation, you get 18x squared equals 200. Divide by 18 doesn't work out great. X squared equals 100 over 9. So x is 10 over 3. And so what is it looking for? You always got to go back to like, what are they looking for?
Mhm.
Well, they're looking for the overall dimensions. So they want the x plus 4. So they want the 10 thirds plus 4, which is 10 thirds plus 12 thirds, which is 22 thirds. And then they want the y plus 8, but we don't have y. Y is solved by 500 over or 50 over x. So you have x is 10 thirds. So it's 50 over 10 over 3 multiplied by the reciprocal. This being 3/5. Is that right? Or is it? No, it ends up being something else. It ends up being 15. Does that seem right? Doesn't seem right. 50 over 10 thirds. Or 50 over, yeah, it's 10 thirds, right? Yeah, 50 over 10 thirds. Do you have a calculator handy? I'm gonna try and this doesn't seem right.
Uh, I don't have my actual calculator with me now.
It's okay. Yeah, let me get one up here. Everything was taking longer today. 50 over 10 thirds. Yeah, it's 15. That one seems really big though. Okay. Ends up being 15. 15 plus 8 is 23. I guess those are your dimensions. But that doesn't work. 23. No, 15 times that doesn't work. Okay. So 15 times 10 thirds is 50 like we want. Okay. So those are good. Those are the border dimensions. Any questions on that or anything to clarify?
Um, no, I don't think so.
Okay. What else would you like to cover? I think that was everything you sent over.
So problem that we did was from the back side of a page, but
Oh, no,
we have
there's more.
two more
There's more.
problems on the other one.
There's the balloon and which is function increasing, decreasing, and then a rectangular patch. Okay. All right. Let's keep going here. Number 4. Right. The balloon is rising vertically above its sea level. Level straight ground at a rate of 1 feet per second. Distance of the balloon is 65 feet above the ground. A bicycle moving at a constant rate of 17 feet per second passes under it. How fast
I
is
think
between the bicycle?
I
Question.
think we did do, but we didn't do 5 or 6. But I'm good with just doing 6 because I think I understand 5.
You sure?
Yeah,
Okay. You do not want us to do this problem then?
we did this one.
We did?
Uh, was This one was the parabola one, right?
No, no, this is a new
Oh,
problem.
oh, okay. That was number three. Sorry about that. Yeah. Then can we do this one and then number
Of course.
six?
Yeah, of course. All right, so the balloon's going up, and then the bicycle's going to the right. So 3 seconds later, okay, so the balloon was 65 feet. But then 3 seconds later, it's moving at 1 foot per second. So it's gonna be now 68 feet. Bicycle is moving at a rate of 17 feet per second. 3 seconds later, it's at 51. And then we care about how the distance between them, how long is that changing? So we know that this dimension here is 17. And this is 1. That's x prime or dx dt, and that's y prime. Now your overarching equation here is that x squared plus y squared equals d squared. So this time we do have to take a derivative with respect to all of them. So it's 2x x prime plus 2y y prime equals 2d d prime. And we're interested in solving for d prime. 2x x prime plus 2y y prime over 2d. And the 2's cancel. So we have x prime plus y prime over d. And so we have these values. We have x is 51, x prime is 17. So we have, this is x, this is y prime. We've got everything. So we got 51, 17, y was 68, times 1. And then to get d, we don't have d, but d is the hypotenuse. So we know that it's 51 squared plus 68 squared equals d squared. And so your d is the square root of that, like that. So you can either just put that in or for it, put it in now or wait till the end to put that number in.
Um, Probably put it in.
Okay. I don't know if it works out nicely. Yeah, it actually does 85. So the bottom is 85. All right, so it's 935 over 85, which actually works out to 11, believe it or not.
I did not think that was gonna work out like easily.
Yeah, these are pretty carefully chosen. So, all right, number 6. Units here also. So let's see here. Distance is feet per second, so units are pretty important. 11 feet per second. All right. A 216 meter squared rectangular pea patch is enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the other sides. What dimensions for the outer rectangle require the smallest total length of fence? How much fence will be needed? There's a couple ways to draw it. You can either go this way. It's option 1 here. And this is x, and x, and this whole thing is y, and y, or more, what's probably a better way to do it is actually treat the individual segments as y. Or you could do it this way horizontally. X and X, Y and Y and Y. Is there one way you see it versus another?
Um, Probably the second one.
Okay. So the one on the right here, we know that the total area is 2x times y, and that's 216. Is that clear?
Yep.
All right. So now we can say that the amount of fencing we need is y plus y plus y, which is 3y, plus 4x equals, well, that's how much fencing we need. That's the total amount of fencing. So we would normally take a derivative of this, right? But we have two variables. That's where you should go back and solve for one of these other variables. So I'm going
Hmm.
to suggest we solve for y. So y is equal to 216 over 2x, which is 108 over x. 3 times 108 over x plus 4x equals f. So that's 324 over x plus 4x equals f. So now you can take a derivative. F prime is minus 324 over x squared plus 4, set it equal to 0. Solve for x, so you have 324 equals 4x squared. Divide by 4. Thing gonna work? Yeah, x squared equals 81. X equals 9, plus or minus, but obviously it's the positive one. So now you got to go back and get y. So y is 108 over x. 108 over 9 is 12. So those are the values of x and y, but you got to go back to your drawing and put in the right values. All right, so y is 12, 12, 12, 12. X is 9 and 9. So the dimensions are 12 by 18. And then in terms of how much fencing is needed, you got to go back to the equation for the fencing, which is right here, right? You know, 3y plus 4x. It just depends on what they ask for. They can ask you for a bunch of stuff. So it ends up being 3 times 12 plus 4 times 9. 36 plus 36 is 72. It's meters, I guess. Meters. We've got some time left. Do you want us to go through number 5?
Sure.
All right. Okay, find the intervals in which the function is increasing, decreasing, concave up, concave down, local extremes, and inflection points. Let's start by taking a derivative here. Minus 3x cubed plus 12x squared minus 4. Something about this doesn't look right. Are you sure this isn't like an x squared?
Um, Honestly, I'm not sure because in the thing it does not say so.
It doesn't say so. Let me graph it here because it doesn't like I don't know. It's a really hard one to solve. Let me graph it, see if I can make something of this.
Okay, thank you.
Yeah, so are you allowed to use are you supposed to use your calculator for these?
Yes.
Oh, you are?
Yeah.
Okay. Well, okay, well, let's keep going here. So for the second derivative, ends up being minus 9x squared plus 12 equals 0. And you can solve for x. X is plus or minus the square root of 4/3. And you would want to make a sign chart for that. Okay. So you could test points in the second derivative here. Like yeah, I don't know, like 0 is a good one, maybe -10 and 10. But you'll find that's negative, positive, negative.
Hmm.
So each of these are inflection points. But then those go back into the um, original if you need the ordered pair, which I don't think you need, but that's what it says here. This also tells you where it's concave up or down. So it's concave down from minus infinity to minus square root of 4/3, comma square root of 4/3, comma infinity. And concave up from minus square root of 4/3 to square root of 4/3. Now, in terms of the increasing, decreasing, the reason I was asking you to use calculator because normally the derivative is such that you can find them, but not in this case.
Hmm.
Let me snip in the graph so you can see what it looks like. Right. So the graph here shows that there's like a relative max and a relative min and a
Hmm.
relative max. So it's increasing. We want to label each of these x values minus 0.532. Again, I don't know how you find that without a calculator. 0.653 and 2.879. You can see that it's increasing, going up into the right, decreasing, then up into the right, and decreasing. It's like that.
Okay.
And then you could say where, plus is increasing, minus is decreasing. What else do you need to find? Local extreme. So we already said that. If it changes from plus to minus, it's a local max. Minus to plus is a local min. Plus to minus is a local max. All right. I do think that is everything here. What other questions do you have?
Um, I don't think I have any questions. You explained it very well.
All right. Definitely, definitely not sure that I did, but I did my best. Anything else you'd like to cover here? We got a little time left if you'd like.
No, I don't. Not today, no.
Okay. How do you feel heading into your exams?
I feel good. I did know like mostly how to do these problems. I just needed a little like push to make sure like I was doing them correctly.
They are all the classic ones, so if you rework them, you'll definitely see them on the test. I mean, that's my experience.
Hmm.
We didn't see anything different than what you normally see. So,
Hmm.
all right, so well, that's it. I will definitely stop here for today.
Thank you.